Hello everyone, this video is to give you a proper idea about our final year project, which is emulating a computing grid in a local environment for feature evaluation. Before we start, let us explain to you what grid computing is and why it is important to the scientific field. Grid computing is a computing infrastructure that unites multiple computing resources from various locations to work together towards a common goal. This approach results in a high-performance computing grid capable of performing complex calculations in significantly less time. One prominent example of grid computing in action is the worldwide LHC computing grid, WLCG, utilized by CERN, the European Organization for Nuclear Research, founded in 1954. Renowned for groundbreaking particle physics research, CERN used the WLCG to revolutionize computational capabilities, efficiently processing and analyzing massive data from experiments like those with the Large Hadron Collider. Let's identify the problem here. Computational grids, with diverse components in various locations, pose challenges for testing new features in limited local development environments. Deploying updates incrementally from a few sites often leads to failures due to insufficient testing, extending deployment times over weeks, a major issue we're addressing. Computational grids are complex systems with heterogeneous components spread across different locations. Testing and evaluating new features or software on these grids in a development environment with limited resources is impractical. Updates and features are typically deployed in stages, starting from a few sites and expanding gradually, often resulting in deployment failures due to inadequate testing, necessitating restarts and prolonging the process over weeks. This highlights the significant challenge we aim to resolve. What are the existing solutions? A simpler solution is to emulate the entire grid in a local environment to evaluate new updates and features, right? However, this approach requires extensive resources and may be overkill for evaluating specific features that involve only some components and services from the production grid. The optimal solution is to emulate only the necessary components and services of the grid to evaluate targeted features in a local environment. Given that computing grids generally share similar core components, such an approach for specific features in a computing grid can be extended to evaluate general features across various computing grids. The methodology for the suggested solution is as follows. First, identify the necessary components and services from the grid to emulate locally for evaluating the targeted feature. The suggested approach to emulate these features involves using Docker containers. Components are simulated locally using Docker containers. Next, develop a test suite to evaluate the new features using the emulated setup. Subsequently, implement an automated script setup to handle tasks from image building to evaluating the grid setup using the test suite. Finally, set up CI/CD pipelines to initiate the emulation, conduct tests, and display results when new changes are pushed to a repository. These pipelines create a virtual environment to run the setup and execute the test suite automatically. This approach allows developers to push new features or changes and quickly assess their impact, ensuring the healthiness of the setup and reducing deployment failures and overall production deployment time. We applied our methodology to emulate the CERN A-List computing grid in a local environment to evaluate its job submission feature. We have identified G-Central, computing elements, shed or batch queue, storage elements, and worker nodes as essential components to evaluate the targeted feature. To emulate these components locally, we are using separate Docker containers for G-Central, computing element, shed, storage element, and a worker node. The Docker images used for emulation are identical to those used in production, ensuring compatibility with the production grid. These selected components are also common in other computing grids, albeit with implementation-level variations. This approach can be adapted for evaluating features on other grids with necessary adjustments. We utilized Jalian Setup, an earlier attempt to emulate some components of the Alice grid locally, and made necessary improvements to achieve our objectives. Let's discuss the test suite architecture. First, we will conduct necessary tests to evaluate the local environment and the emulated components. Once the grid is emulated, the test suite will submit a job to the emulated grid and verify if its execution proceeds as expected. We use 3 levels of error testing: minor, warn, and critical. If a minor or warning error occurs, we will display a log indicating the error and, if possible, suggestions to resolve it, but we will continue the testing process. In the case of a critical error, we will display logs similarly, but we will halt the execution of the test suite. The entire process, from starting the emulated setup to running tests and displaying results, is automated through Bash scripts. With just one command and optional flags, developers can execute these tasks conveniently and flexibly. Finally, let's focus on the CI/CD pipeline. CI/CD pipelines run across 3 different repositories. Below, we can see the workflow for the Galion repository, which aims to ensure that new changes and updates to the Galion codebase are safe. Initially, it sets up the development environments, clones the Jalian setup, starts the emulated setup, clones the test suite, and runs tests. This process is achieved through a GitHub workflow CI/CD pipeline. Additionally, two similar pipelines are set up to evaluate new changes in the Galeon setup and test suite codebases. The rightmost workflow is scheduled to run as a weekly cron job. It builds Docker images and updates the CERN registry based on new changes in the Galeon setup and production Docker images. This ensures that these built images are compatible with both the Galeon setup and production component images. After implementing in Test Suite and CI/CD pipeline, we thought to improve the developer experience more by adding a presentation layer to the Test Suite. This is a simple React app which includes basic configurations and capable of running Test Suite and view the test summary. Here, we start the entire setup with a single command. This means developers don't have to worry about setting up the local environment and can focus on development. Next, we'll run the test suite. As you can see, it provides a real-time detailed report in the terminal, indicating the test status and highlighting any issues. This is the web interface we implemented to simplify the testing process by adding a presentation layer to the test suite. With this, developers can run a test suite by a one-click and view the test summary in real time. This video provides an overview of our final year research and development project, which focuses on emulating a computing grid in a local environment for feature evaluation. Grid computing combines multiple computing resources from different locations to perform complex calculations efficiently. We address the issue of lacking a feature evaluation environment by isolating and emulating individual components, using a containerized approach. Additionally, we enhance developer productivity by implementing a comprehensive test suite and automating it within the codebase using CI/CD pipelines. This setup simplifies local environment management and ensures thorough testing, allowing developers to focus on development while identifying and addressing potential issues effectively.